I want to thank the organizers for inviting me to talk, and also I want to thank you for your perseverance. I know workshops and meetings like this tend to be more like an Ironman event where you've got the 2-mile swim on the first day, you do the 100-mile bike right after breakfast on the second day, and then you've got a marathon in front of you for the afternoon. So thank you for your patience. A bit of a Monty Python notion of now for something completely different. We've heard about big data, we've heard about exascale, we've heard all about applications, and there's been no real talk about facilities to date. So maybe the last 2 talks here were saving the best for last, but I'll leave that for you to decide. So I'm Steve Hammond. I'm the Director of Computational Science at the National Renewable Energy Lab. We are a DOE lab, and we're located just outside of Denver. Our sponsor is the Office of Energy Efficiency and Renewable Energy. And I'm not going to talk too much about our applications of wind and solar and renewable fuels, but more how we've applied our expertise in energy efficient buildings and taken an approach towards data centers. So why should we talk about data centers here? They're highly energy intensive facilities. Our data center was built around the notion that we would support about 1 kilowatt per square foot. That's about 10 to 100 times more than a typical office space setup is. We'll find server racks in HPC especially well in excess of 30 kW. Power and cooling constraints are increasingly dictating what we buy and what we can do. The EPA is estimating that about 3% of the total electricity generated in the US is going just to data centers. And also there's surging demand for data storage, cloud and web services, and extreme scale computing. And I happened to notice in the paper yesterday morning that Amazon is planning to build a massive AWS data center in Dublin, Ohio, and spending $1.1 billion. So, computing continues to grow and the demand for the services and capabilities. So if we're not careful and you don't have a carefully designed data center, you can be spending more on the infrastructure to support your computing than on the computing itself. I borrowed a slide from a good friend of mine, Mike Patterson at Intel. I think he does a great job of summarizing what's going on the IT side and why we have to pay more and more attention to the data center proper. In terms of technology trends, they're packing more and more cores onto a die. There's die stacking, it was mentioned yesterday, putting memory stacked in the packaging and bringing that close to whatever your processing unit of choice is. There's greater integration of fabric, advanced switches, bringing things all to higher density. Haven't heard any talk at this meeting about silicon photonics. That's very promising technology. It's low cost, very promising performance, but thermal issues there do exist. All of these start to bring about a perfect storm where we're getting higher and higher power densities in our racks. So whether you're on this side of the pond or the other side, you're looking at high power distribution to your racks, 400 or 480 volt AC, 3-phase. Density and weight of your racks is going to push the limits of your facilities and structural challenges. And cooling, probably the biggest challenge we face is if we're looking at 50 to 100 kW racks is how do you get the heat that's generated from inside these refrigerator size volumes? How do you get that heat efficiently out? So this is what I wanted to focus on. So what happens is from an energy efficiency side within data centers is the choices we make on the IT side of the power, the packaging, the cooling, and the energy recovery in the data centers drives our TCO. So that's the total cost of ownership, not just what it costs to buy the initial computer that we're going to use. And why should we care? Because this impacts our carbon footprint, our water usage, limited utility power. So depending on where you site your data center and how it's operated, all of these things are going to come into play. Where we are in Colorado, we pay roughly $1 million per megawatt year. And I've managed to wrestle get good organizational alignment. So money I save on the facility side, I can actually plow back into resources such as staffing and more compute equipment. again, if you have an inefficient data center, your OpEx may exceed the cost of your IT equipment. From a space standpoint, we can use much less space if I have 10 100 kilowatt racks than if I spread that out and had 20 kilowatt racks. I would need space for 50 racks. We've recently had a visit to our data center by Visa, the credit card company. They have a 60,000 square foot data center and they're looking to renovate that. But their average rack density right now is 3 to 5 kW. So they were like, we could either retrofit a great big facility or we could go to the much smaller one, and if we go to higher density racks and we use different components, what's that going to look like? So we're helping them look at the total cost of ownership and return from a balance of IT and facilities. Most sites have a fixed electrical supply, and as time goes on, that becomes a constraint. So it's very expensive and disruptive to add more power to your facility. And if you've got a certain amount of electricity coming in and that becomes a hard boundary for you, the more of that utility, the more of those electrons that have to go to supporting your infrastructure versus going directly to your IT equipment, that becomes a bottleneck for you. So a less efficient data center steals power and dollars that you could otherwise use for compute capability. So you want to minimize the investment in facility and operating expenses and maximize your approach to computing and staffing. So we've taken a holistic view of computing, of the whole computing enterprise. We started with a brand new facility that was commissioned just a little over 2 years ago. Our considerations were on the power distribution. Are you distributing 208 or 480 volt? What is your ambient temperature? So that'll determine whether or not you need chillers. Your approach to cooling, are you going to use air? Are you going to use liquids? And where does that heat exchange for your IT equipment occur? Does it occur by a crack unit that sits outside at the perimeter of your data center? Are you doing it at the rear door of your racks? Or are you going to do component level cooling? Ed had the tray out here from the HP Apollo. Are you going to do it right at the components? And then for your waste heat, are you going to declare victory to get the heat to the back of the rack and say, job well done? Is it going to be liquid or air? Certainly 90-degree air has fewer opportunities for reuse than 90-degree water. So are you going to use it or are you going to throw away? So all of these things from a holistic view of a data center, from the computing enterprise. Look at your whole facility, not just buying the next system. So as was mentioned yesterday, this came up during the disruptive technology round. Liquids are 3 orders of magnitude more efficient than air in their cooling capacity. And the transport of liquids requires much less energy from fans. So I think of it as that a juice glass of water has the cooling capacity of a room full of air. And the pump energy needed to move that juice glass of water around is much less than the fan energy needed to move that the large volume of air. If you take a look at what a typical computer board, what your motherboard looks like, what are the T-case limits of the components? So the CPUs can operate safely up to 149 Fahrenheit, memory at 185. Your GPUs, your accelerators can go up to 167. But a typical data center starts with a chiller outside, right? It cools water down to maybe 45 degrees Fahrenheit. It goes through pipes into your data center. There's a crack unit on the outside of your data center generating with a heat exchanger there, blowing cold air under your floor. You've got cabling, you've got other stuff that accumulates under your raised floor. And then you've got to move tiles around to get it in front of your rack, hoping you have an ambient of maybe 60 in your data center. Most data centers feel like meat lockers. Also, you can keep your components inside to stay below 150 Fahrenheit. I mean, it's inefficient at every step. I've used the analogy, it's like, you have a beverage of choice and it's out on your in a can on your kitchen table and you go outside to start your air conditioner to get it cold. It just doesn't make a lot of sense. So we made the decision in 2006 that we were going to move to liquid cooling, and that sort of drove our data center, drove our consideration in the design for the data center. We thought a lot about liquid cooled doors. Those are good, but you often need much colder supply temperatures than if you did direct component level liquid cooling. So clearly we can do better. Rising power densities do require the component level liquid cooling. Some of the benefits we've seen is thermal stability. The chips themselves, actually, even though we're supplying warmer water, the chips themselves are kept cooler. We find we're in much more opportunities to use turbo mode on our Xeons. You can eliminate expensive chillers if you start with warm water liquid cooling. You also, if you're using warm water, you eliminate condensation concerns. And by starting with warm water and getting hot water back, you have opportunities for waste heat. So let me keep going. ASHRAE has spent a lot of time looking at liquid cooling in data centers, so we don't have to invent it ourselves. So they've got tremendous guidelines that you can use for reference. When we had air cooling explicitly, you have to worry about humidity and fan failures, cable blocks under your floor, mixing in hot spots, top of rack issues. Those go away with liquid cooling. It's not completely worry-free. You do have to worry about water chemistry. I've learned a lot more about water chemistry than I ever thought I'd have to. Think carefully about what kinds of pipes you're using and where, and use plate frame heat exchangers are really effective. They can segregate your water types and minimize what you would need there. Let me see. So one recommendation I would have is that you insist that the vendors follow these ASHRAE guidelines. Otherwise, it could be costly if you have to put in special piping or chemistry or other features. Here's an aerial view of our data center. So here's the whole facility. We have office space for 220 staff. Our data center sits in the middle, and then we have laboratory space off to the back. So our data center proper is 10,000 square feet of uninterrupted usable floor space. It's a 10 megawatt facility. We leverage our favorable climate. We have evaporative cooling only, so we do not have any mechanical chillers involved at all. If you can do that, you take giant strides towards tremendous energy efficiency. It's a LEED Platinum building, and the overall facility, in February, we were recognized by R&D Magazine as Laboratory of the Year. So it's quite an accomplishment. One of the things that we did, we benefited from our approach was it cost us less to build and much less to operate. By going to warm water liquid cooling, we eliminated the need for the expensive and the very energy inefficient chillers. I know many of you in the room have visited. If you haven't been to visit us, please do so. We're not a classified lab. We don't do any classified work whatsoever. So we built the facility as a showcase to share what we've done. And someone said last night, liquids are important, and we just need somebody to be first out of the gate. Well, we've been doing it for almost 2 years now. We did have an integrated chips to bricks approach. We have a plaza area here. Just outside the building, we do get snow in the wintertime, and we're even heating glycol loops under the plaza area there for snow melt. So we eliminate any icing, and it's a safer area. Some of our key data center specs, as I said, we do have warm water liquid cooling. Mike Patterson cringes every time I say that. He wants to remind me that there's actual classifications. So we are a ASHRAE W2 classified data center. So that says specifically what our supply temperatures is, and it gives a range. Water is a much better working fluid than air, and we as built, it's a 2 megawatt facility with room to expand fully to the 10 megawatts. And our primary water circulation is a 40 horsepower pump. So it's not a lot of complicated infrastructure. It's maybe elegant in its simplicity. The other side is we're utilizing waste heat. So we want at least 95-degree water back off of the system. And that was part of the interplay between sort of what we could do using evaporative cooling only and what the building needed for the heating side. So we need that minimum 20-degree difference from supply and return. So we're capturing right now with the HP Apollo system, we're capturing over 90% of the heat load directly to liquid. So our racks are sitting outside in the middle of the room, and they're more or less room neutral in terms of heat. But we do have legacy equipment, so you can't completely eliminate the air side. So from our Lustre file system and networking and control nodes and some miscellaneous servers that we do have 2 full rows that are hot aisle contained. So if you took our data center and viewed it as a layer cake and sliced through the middle, we have our mechanical space down below. It's a 16-foot raised floor, very compact design. Our servers and IT equipment all sit directly above. We have support facility down below because, as I said, we capture the waste heat directly from our system and it's supplied to the building as a primary heat source for the building. And as we expand our system, we actually have plumbing plumbed in place so we can export heat to other buildings on campus. All the pipes are color coded. We've got floor to ceiling windows so you can come in and everything is revealed. So we have a 3D sort of optimization problem. For data center energy efficiency, we all know how to sort of build energy efficient data centers. Then you want to procure the systems that provide the most efficient sort of work per watt that you can. And then on the third dimension is look for ways to reuse the heat that's generated. Right? So you want an efficient data center. You want to procure the systems that will best meet your workload, and then whatever heat is generated, use that. Our early experience with liquid cooling, we've had liquid cooled systems for the last 21 months. We've had 0 incidents. This includes our work with some early prototypes we got from HP early in January of 2013. So we have liquids in the rack, but no water on the floor. Our production racks were delivered last August, and in mid-September of 2013, our HPC system passed acceptance in November. We had 6 weeks of friendly user mode, and it's been in production use since 2014. We've had a lot of interactions with HP and helped on how to design and how to interface the system with facilities. And I think HP would agree this has been a really positive experience for both organizations. I've just put up 3 months of PUE data. That's the power usage effectiveness. Where I checked yesterday, I think it was 1.044, but our sort of trailing 3-month average is 1.05. Right here, we had a facility-wide or a campus-wide power outage. So we're not sort of taking things out and saying, well, that didn't really count. That's actual data where we were shedding workload, but the system was still, and all the infrastructure was still going. So even though our IT load went down, the infrastructure load stayed constant. So, but that's the spike there. But more or less, it just sits. The design point was 1.06 or better, so I think we're doing pretty well. In terms of 3 minutes, great. In terms of ROI, what's the bottom line? I mean, we've done this because it makes sense to us. It's part of our mission. But I think the bottom line is really is it does cost less. So let me see. So on the CapEx side, we didn't build a building that required chillers, so we can eliminate that. If we would to have required chillers, it would have cost us $4.5 million worth of equipment to install, plus the electrical infrastructure to support those. On the OpEx side, if we compared our PUE, our data center with a 10 megawatt load, so that I guess the standard of how these comparisons are made is, look, if you were going to do full build out. So if we compared it a 10 megawatt load and assume we pay $1 million a megawatt, and we compared our PUE of 1.06 with an efficient data center running at 1.3 and a 10-year savings, we're looking at $24 million of savings for our efficiency. And this does not include the savings that we offset by capturing heat and reusing it. This is just on the energy side. We save about $200,000 a year by not having to heat the building from our central plant. So if we add that in, it would be another, over a 10-year span, it would be 26 million. So we have a liquid cooling checklist that we talk about with visitors and others that are interested, starting with the, follow the standards, the ASHRAE guidelines provide an excellent guide if you're looking at liquids. We use in-row cooling distribution units. Those are very efficient ways of managing the heat load and to separate your building water and what water circulates among the racks. It also provides flow control to manage the temperature of the heat of the heat that's returned in your water. If you have filtration in your system, make sure you have a filter bypass so you can change filters without having to take your system down. N+1 redundancy in your hydronic system, so that's for pumps and filters and everything else. We are utilizing warm water supply and providing hot water for maximizing opportunities for waste heat reuse. Minimize your exposure when servicing, so as Ed showed, they can service a node without breaking water connections. Do your heat exchange directly at that heat source. Look for the best, most well-engineered solution you can, and insist that you get 95% of the rack heat load captured directly to liquid. Otherwise, even though it's a liquid-cooled system, you're still going to have to put it in some sort of hot aisle containment. One of the most common questions I ask is, I've got a legacy air-cooled data center, and you had the benefit of building a whole new data center. What could I do to start a transition? And a typical data center does have liquid in it. There's liquid here that goes to your crack unit, and that just generates cold air. So what you could do is put your liquid-cooled system and grab the crack return water, feed that to your liquid-cooled system, and then return hotter water to your heat rejection. So there are fairly straightforward ways to intercept and do that. And a couple final thoughts as the time ticks down. Energy efficient data centers, there's lots of good documentation out there. Just please, apply best practices. It's not rocket science. Separate your hot from cold and ditch your chiller. Raise your temperature. It's really not hard. Don't fear liquids. It can be done very safely, and it's going to be increasingly prevalent as we go to higher power density. Metrics, oh gosh, make sure you've got meters in there. If you're not measuring, you can't manage it. From our perspective, 1 hertz is at a minimum if you want to effectively manage. And what we're looking ahead, there's lots of open research questions. Can we manage workloads within a power budget? If there's time of day pricing, can we shift workloads around to maybe peak shave and do things proactively rather than have to put in hard power caps? And with that, I'll take some questions. Thank you very much. Go ahead if you want.
How hot do you run your disk? You get temperature for CPU memory. How warm do you run your disk?
So our file system sits in the same data center, and depending on the day, it's as warm as 75 degrees.
Okay. And what's your typical Colorado temperature and humidity?
I'm trying to remember today it was 88 degrees and 19% humidity sometime this afternoon.
Okay. But
we do benefit from cooler nights and lower humidity. But our, archive and tape system, as well as all our file systems, all sit in the same room. We just have much higher power density and warmer racks that are fed with the liquid.
But your humidity stays low?
You-
You don't have hydrolysis or anything with tapes?
That's correct. We are adding, we do humidify to control, but it's to keep it, no worse than 20%. To be honest, the biggest challenge is changes in humidity, not any given humidity. So we try to keep it constantly low.
Any other questions?